Thomas Miller here, Applications Engineer from Oxford Instruments. So I presented something very similar to this just yesterday at the ALE conference. Instead of being an all-encompassing ALD, I'm going to be focusing on one of the new developments, which is utilizing RF bias to the substrate. Good. It's not done. Sorry, just a moment. This is a collection of experiments carried out by Agnieszka and E and myself, and under the same methodology, and then brought together and presented here for the second time this week. And this is looking at a new control for your ALD films, utilizing the RF bias to deliver different characteristics, specifically determining stress. So, primarily we're looking at stress in relation to increasing RF bias, but also I report about the RI and the growth rate. Stress in thin films can be important for a whole range of applications. Here's two prominent examples. Delamination and flexible substrates can be affected by it. Due to the thinness of ALD films, stress is a relatively unexplored characteristic, even though amorphous thermal aluminium oxide has long been known to have relatively high stress levels. It seems not to be. Sorry, it's not changing on one screen and not the other. Shift F1. Okay, I might have to do that a bit of an odd route, but stress control has been looked at and compensated for in PECVD using two routes. One is the addition of helium flow to your process gases, and the other is a alternating sequence of low-frequency plasma power and RF plasma power, hopefully like the one you're seeing down at the bottom in the graphic. These are two examples where you can see that the stress moves across from compressive to tensile. And at that point, you can therefore determine that you're able to tune your process to deliver low stress. And it's not moving on my screen. Yeah. Okay. So, introducing that into the ALD cycle. This is just a common ALD cycle for plasma-enhanced ALD. And this is being applied within, let's get the buttons instead. Within this section here. So throughout the plasma step, which is usually an ICP power, we're also applying the RF bias. Is it going to do it? I'm sorry, this is... No, it is not. Okay. Okay, I'll have to work from without the notes so you can get a better presentation. So that was within the ALD cycle. This is physically within our tool. This is our standard offering of a flex cell. And you can see from this we have our usual ICP source delivering plasma gases alternated with your precursor, bringing the two half cycles together to deposit your material on your substrate at a particular temperature, and all controlled by an APC to deliver particular pressures that you're interested in. Did it move? Good. So the addition of RF bias to your table creates what we call a plasma sheath, which is then interpreted as being a DC bias of somewhere around hundreds of electron volts. This detail here, you can refer back to some of the other presentations, specifically my colleague Agnes, who was working on the etch side of DC bias, and that was presented at the Baltic conference a couple of months ago. But let's have a look. The experiment itself can be defined here. We're specifically looking at tantalum oxide, titanium oxide, molybdenum oxide, and tungsten oxide. These are just the general features, Woolham being the measurement for the thickness, uniformity, refractive index, and we do the Toho technology FLX for the stress. The other key thing here is we're growing to thicknesses, or we're targeting thicknesses of 20 nanometers. Okay, to the results. You can see here, this is our tantalum oxide. We're using TBTDET precursor at table temperature of 90 degrees. So with zero DC bias, we have a tensile film, as you can see it, but the addition of DC bias creates a compressive film. And then potentially you can kind of see it beginning to level out. This is a similar idea when you get to titanium oxide using TD mat precursor at table temperature of 300. Again, it starts at tensile and moves to compressive. Third example we have here is tungsten oxide, and this is BTB MW precursor and 300 degrees. On the difference here is that we start with a compressive film and it progressively gets more compressive. So for me, this would be ruled out just because it is already starting at a negative value for stress and increasing. So therefore, you would not be able to tune it to be low stress, as this is the limit of where you can apply DC bias. Slightly more elaborate, I've then looked at molybdenum oxide at 2 different temperatures, and you can see that it has a similar trend to the tungsten oxide in this one, but the change in temperature from 140 degrees to 200 degrees, the 200 degrees one you would be able to deliver a low stress, whereas the 140 degree one you would not. These have shown to me to be quite interesting results, in that you are able to, this has shown that you have the capability of delivering low stress in certain applications, certain materials. Summing up some of the other results, you can see that generally, these are the green lines, that the growth rate is usually going up, although tantalum oxide disagrees with this. Refractive index tends to stay the same across the board, but that would not necessarily be conducive to our thoughts, which is with increasing DC bias, you would have a densification of the film, but whereas we're seeing here is relatively straight lines. Summing up, this is a relatively short presentation. We've seen that DC bias is able to deliver you low stress materials. There's still some work to be done in gaining an understanding of the growth rate and refractive index portions of this, with more characterization, which and chatting to a colleague yesterday from Eindhoven, they have a better grasp of this as they've been doing some more characterization. TEMs have been able to show them that the addition of DC bias is going to create imperfections within the film, and that actually is increasing the thickness, the growth. But the work that I've carried out is kind of summarized here. Stress, yep, generally it's all lowering of the stress within the materials that I looked at. Some are able to be actually tuned to deliver low stress, some not. But that kind of brings me to the end. Some special thanks to Mike Cook and E, who were not mentioned at the beginning, and our applications group, who not complete, but that's a good chunk of them. Thank you very much. Any questions?
Any questions? Yes.
Did you not try two temperatures for a constant precursor?
At the time I had available, it was just the one temperature. So I've been a little bit limited on the scope of what I've been able to do, basically. So yeah, there's a lot of potentials out there, different temperatures, more of a wide range, a lot more data points, but at the time available to me, not possible. It would be interesting to do all of those multiple different temperatures to really get a grasp of what's going on, and it would potentially give us a more clear idea about what's going on with the refractive index and growth rate.
I was wondering, well, two things. One, how do you measure the stress? These are very thin films. So what's the method that you've used?
The method is, go back, it is using the Toho, that one. It's a laser which scans across the wafer before deposition, then you deposit, and then it scans it again. And this, with the Stoney formula, it's able to determine what the stress induced into that wafer is. There is, though, fundamentally some limits to that. The film thickness here is only 20 nanometers. Ideally, you would go 2, 3, 4 times thicker than that to get a really solid result for that, though. But this is ALD, and thin films are where we work.
Mm-hmm. So do you have a feeling for how much uncertainty is in your data then, given that? I mean, I would be concerned.
Yes. Needs to be run a lot more times, okay. Ideally thicker films to give us more of a greater confidence in the results. Thankfully, just before my presentation yesterday, a gentleman from Eindhoven, Tarsin, presented actually this graph, and it very much matched what I had. So that was pleasing to see, even if I knew that there was potentially some error in there. Just more work is needed. It's a new area, and these are our initial results.
Do you, I mean, not being that familiar with stress control in ALD, what are other methods that people have explored that you're aware of for stress control in ALD? Besides the plasma enhanced RF,
Yeah. So, sorry, is there other methods of characterizing or?
No, of producing, of controlling it.
This, I'm not aware of any others.
Okay.
Classical one, you change pressure, so you change the ion energy to the surface. Yeah. Mm-hmm. But the ion energy to the surface is so low in the air,
right.
Anyway, you're not going to change it by
very much, right.
But the other thing that you potentially might see here is you see the change in crystal, crystal formation as well, which might be very interesting. And there is a paper that we did, which they didn't present yesterday, but does show with dioxide you can see it.
In titanium dioxide?
You can change the titanium from anisi to rutile or rutile.
I see. That's for very thin films, though, right? Because it's crystalline. Yeah. Okay.
Likewise, potentially temperature is an influence as well.
Mm-hmm. Okay, great. Well, thank you, Thomas, for the talk and for keeping us on time now. So we're on schedule for lunch. Lunch will be